Welcome to the peaceful space of sleep-friendly science, where we journey back to a time before life, to a quiet, ancient world simmering with a profound and beautiful secret. Tonight, we drift across 4 billion years to wonder about the greatest mystery of all, the first spark. Imagine a young planet of volcanic warmth and primordial oceans where the first whispers of existence were just beginning to stir. How did simple, non-living matter learn the secret to becoming alive? Now, settle in, take a deep breath, and let the soft sounds guide you as we begin tonight's journey into the unknown. Section 1, The Primordial Canvas. And so, our journey begins. Let your mind gently detach from the here and now. Feel the weight of the day dissolve as your consciousness sinks, soft and slow, through the immense, dark waters of time. We are not traveling through space, but through ages, descending past millennia, past epochs, past eras. The familiar sounds of your world fade into a distant hum, replaced by a deep and resonant quiet. We are going back to the very beginning. Back 4.5 billion years to a world you would not recognize, a planet in its violent, beautiful youth. Drift with me now and open your mind's eye. Before you hangs a world suspended in the blackness of space, but it is not yet the gentle blue marble of modern postcards. It is a glowing ember cooling in the dark, a bruised pearl of rock and fire. This is the young Earth in an age geologists call the Hadean, a name borrowed from the underworld of ancient myth, and for good reason. It is a place of breathtaking chaos and profound creative power. Look up at the sky. It is not the familiar, welcoming blue we know. It is a thick, heavy, amber veil woven from carbon dioxide, nitrogen, water vapor, and perhaps a haze of methane. The sun, younger and fiercer, shines through this dense atmosphere not with a crisp, white light, but with a diffuse, ominous, reddish glow. And hanging in this strange sky is a constant, looming companion, the moon. It is so much closer to the Earth than it is today, a pockmarked giant filling your field of vision, its gravitational pull a physical presence, a silent hand stirring the world below. It exerts a monstrous force on the young oceans, creating tides of unimaginable scale, great mountains of water that sweep across the globe with relentless energy. Now let your gaze drift downward to the surface of this nascent world. There are no continents as we know them. No sprawling plains, no ancient forests, no gentle, rolling hills. Instead, the planet's crust is a fractured mosaic of black volcanic rock, islands of freshly cooled magma rising from a global ocean. Great plumes of smoke and ash billow into the heavy air from countless volcanoes, their fiery mouths glowing in the dim light. These are not mere mountains, they are the planet's slow, rhythmic heartbeat made visible, the very conduits through which its molten core breathes fire and steam, building the first land masses, one basaltic layer at a time. The air is filled with the constant, distant rumble of their activity, a bass note in the planet's first symphony. And the rain, it is always raining. But this is not a gentle, life-giving shower. The superheated atmosphere is saturated with water vapor which condenses and falls in torrential, near-boiling downpours. As this hot, slightly acidic rain strikes the searing volcanic rock, it creates a perpetual hiss, a global sizzle that is the sound of chemistry in action. It is the sound of rock dissolving, of minerals being leached from the fresh crust and carried away on their journey to the sea. Every drop of rain is a tiny messenger, carrying bits of the land into the water, a slow, patient erosion that has already been happening for millions of years. Beneath the sound of the volcanoes and the hiss of the rain, there is a silence. A silence so deep and complete it is almost a sound in itself. It is the profound, unbroken quiet of a world without life. There are no birds to sing, no insects to buzz, no creatures to call out in the twilight. There are no leaves to rustle in a non-existent breeze. There is only the raw, elemental noise of geology and weather. The crash of colossal waves on jagged shores. The groan of the cooling crust. The whisper of steam escaping a fissure in the rock. It is the sound of a stage being set, magnificent and grand, but utterly empty. The actors have not yet arrived. Let us now sink beneath the waves of that tumultuous ocean. Let your awareness drift down, past the churning surface into the deep. The water here is not blue and clear. It is warm, perhaps even hot, and tinted a murky, dull olive hue by vast quantities of dissolved iron. It is a planetary womb, a vast, warm, chemical broth rich with the minerals washed from the land and the gases dissolved from the atmosphere. This is the famous primordial soup, a term that sounds almost quaint, almost cozy, but here, in this immense, dark, and turbulent ocean, it feels like a cauldron of infinite possibility. It is a liquid laboratory stretching across the entire globe. Here, in this water, are the ingredients, the fundamental building blocks, forged in the hearts of long-dead stars and delivered to this world by comets and asteroids. Let's meet them, not as abstract symbols on a chart, but as the quiet protagonists of our story. There is carbon, the great connector, the ultimate socialite of the atomic world. With its 4 bonding arms, it has the unique ability to link up with other atoms, including itself, forming long, complex, stable chains. It is the ultimate architect, capable of building the intricate molecular scaffolding that will one day become life. Right now, it floats idly, perhaps in the form of methane or carbon dioxide, unaware of its own potential. There is hydrogen, the universe's simplest and most abundant offering. Small, light, with just one connection to offer, it is the universal companion, readily bonding with other elements, completing their structures, adding itself to the great chains that carbon will build. There is nitrogen, the stoic partner. It forms strong, stable bonds, crucial for the backbones of the most important molecules to come. It brings a quiet strength, a reliability that will be essential for creating structures that can last. And there is oxygen, the fiery dancer, an atom of immense energy and reactivity. For now, most of it is a prisoner locked tightly in water molecules, H2O, or in the silicon oxides of the rock. Its wild, transformative energy is contained, waiting for a key to turn the lock. These atoms and other phosphorus, sulfur, iron are all here. They drift and jostle in the warm, dark water. They are bounced around by the thermal energy of the ocean, colliding for a moment before recoiling, moving on. A carbon atom bumps into a group of hydrogens. A nitrogen drifts past. It is a dance of pure chance, of random, meaningless encounters. There is no intention, no purpose, no memory. They are like individual letters floating in a vast, liquid jumble. The potential for a language is there. All the characters of the alphabet are present. But there are no words yet, no sentences, no stories. This is the world before the spark. A planet of raw energy and raw materials. A canvas stretched and primed, painted with the dark colors of rock and ocean and the fiery hues of volcanoes. The silence of non-life is the silence of anticipation. The random dance of the atoms is a dance of waiting. Everything required for the great masterpiece is here, but the artist has not yet begun to paint. The orchestra is seated, the instruments are tuned, but the conductor has not yet raised the baton. The secret of existence is locked away and the key has not yet been found. The first question is not just how life began, but how this magnificent, chaotic, and empty world could even begin to ask the question. Section 2, the energetic spark. The stage we have set is one of immense, quiet potential. A world of ingredients, adrift and waiting. But a kitchen full of ingredients, no matter how fine, will never produce a meal without a chef, without a source of heat, without a spark of energy to begin the transformation. The inert atoms of the primordial ocean were locked in stable, comfortable arrangements: water, nitrogen gas, methane. To break these bonds, to coax them into new and more interesting partnerships, required a force, a jolt. It required the universe to reach down and stir the pot. And on the young Earth, this energy was not scarce. It was everywhere, in forms both magnificent and terrifying. Let your focus drift upwards again, back to that thick amber sky. The air is heavy, turbulent, a constant clash of hot and cold, wet and dry. And in this churning cauldron of gases, titanic forces build. Watch now, as the sky darkens not with twilight, but with an impending fury. Static charge accumulates on a scale we can barely comprehend, and then it is released. A bolt of lightning, thicker and more powerful than any you have ever seen, tears a jagged, momentary scar of brilliant white-blue light across the sky. For an instant, it illuminates the churning clouds and the black waves below. It is not a single flash, but a rapid, stuttering cascade of energy that spiders across the heavens, followed not by a distant rumble, but by a deafening, world-shaking crack that vibrates deep within your chest. This is not a rare event. Storms like this are a constant feature of the Hadean world, a global, unending electrical convulsion. But this lightning is more than just light and sound. It is a celestial blacksmith's hammer. In the billionth of a second that the bolt exists, its channel reaches temperatures hotter than the surface of the sun. Within this superheated path, the simple, stable molecules of the atmosphere, the nitrogen, N2, the methane, CH4, the water vapor, H2O, are ripped apart. Their strong, comfortable bonds are shattered instantly. The individual atoms of nitrogen, carbon, hydrogen, and oxygen are, for a fleeting moment, liberated, flying free in a plasma of pure energy. And then, just as quickly, the channel cools. In the chaotic aftermath, these newly freed atoms do not have time to find their old, familiar partners. They frantically grasp for the nearest neighbor. A carbon might find a nitrogen, forming a cyanide group. A carbon might bond with an oxygen and some hydrogens, creating formaldehyde. These are no longer the simple, inert gases of the old atmosphere. They are new things. They are reactive. They are what chemists call precursors, the first simple, essential building blocks. Molecules that carry a little spark of the energy that created them. And now these new creations, heavier than the surrounding air, begin their slow descent. Carried by the torrential rains, they fall from the skyforge into the vast, warm ocean below. A gentle, persistent rain of possibility dusting the global cauldron with the first hints of complexity. A continuous gift from the violent sky. This is not just a theory, it is a process we have recreated in our own laboratories. In a famous experiment, scientists passed sparks through a flask containing the gases of the ancient Earth, and within a week, the clear water at the bottom had turned a cloudy, reddish-brown, rich with amino acid, the very building blocks of proteins. The lightning was not just a destructive force, it was a profoundly creative one, a violent artist painting the first strokes on the primordial canvas. Now, let us consider another source of energy, one more constant and pervasive than the lightning. Turn your gaze back to the young, red-tinted Sunday. It hangs in the sky, a constant source of light and warmth. But this light carries with it an invisible, potent force. Without a protective ozone layer, which would not form for billions of years, the young Earth is bathed in a relentless, unfiltered torrent of high-energy ultraviolet radiation. Imagine this UV light not as the gentle warmth that tans your skin, but as a constant, silent, energetic rain, a shower of invisible arrows striking the surface of the world. It penetrates the upper layers of the ocean, a tireless engine of change. Just like the lightning, this energy is strong enough to break the chemical bonds of the molecules floating in the shallow waters. It can split water molecules, liberating reactive hydrogen and hydroxyl radicals. It can energize the simple carbon compounds, nudging them, encouraging them to react. Picture a shallow tidal pool on the shore of a black, volcanic island. The colossal tides have receded, leaving behind a small, isolated body of water. Here, the sun's energy is concentrated. The water is warm and the UV radiation pours down hour after hour, day after day. As the water evaporates under the sun's glare, the chemicals within become more and more concentrated, bumping into each other more frequently. The sun's energy provides the necessary push, the activation energy to overcome their reluctance to react. New bonds form. Simple chains begin to grow. The sun is a gentler but more persistent chemist than the lightning, patiently working away in countless such pools across the globe, conducting a million slow experiments under its unwavering gaze. But perhaps the most profound spark was not ignited in the sky or on the sunlit surface. Perhaps it came from the deep, dark heart of the planet itself. Let us sink once more, down, down, down through the murky, iron-green ocean, deeper than sunlight can ever reach, into a realm of crushing pressure and absolute blackness. The water grows colder, the silence more complete. But then, Ahead of you in the dark, you perceive a shimmer, a strange, ghostly oasis of warmth and activity in the abyssal plains. You are approaching a hydrothermal vent, a crack in the ocean floor where the cold seawater has seeped deep into the planet's crust, been superheated by the magma below, and is now being forced back out into the ocean. But it doesn't return empty-handed. On its journey, it has become a hot, acidic, and profoundly changed fluid, saturated with dissolved minerals, gases, and metals leached from the hot raw hydrogen, methane, sulfur compounds, iron. As this superheated, chemical-rich fluid erupts from the vent, it looks like a plume of black smoke, giving these structures their name, black smokers. It billows upwards into the cold, alkaline seawater. And at this interface, this meeting point between two profoundly different chemical environments, a storm of chemistry is unleashed. The sudden change in temperature and pH causes the dissolved minerals to precipitate out of the solution, building up over thousands of years into vast, porous, chimney-like structures. Imagine these chimneys, not as solid rock, but as intricate, porous sponges, riddled with a network of microscopic pockets and pores. Each tiny cavern is a miniature, protected laboratory. Here, inside these warm, mineral-lined chambers, the simple molecules from the vent fluid and the surrounding ocean become trapped and concentrated. The mineral surfaces themselves, rich in iron and sulfur, act as catalysts, like tiny workbenches, holding the molecules in place and encouraging them to react. The flow of vent fluid provides a constant gradient of energy and raw materials, a chemical battery that runs continuously for centuries. Here, protected from the destructive UV radiation on the surface, in a stable, warm, and energy-rich environment, the slow, patient work of creation could proceed uninterrupted. It is a deep-sea kitchen, gently simmering the primordial soup, allowing more delicate, complex structures to form and persist. A place where the first whispers of chemistry could grow into a conversation sheltered from the chaos of the world above. So, you see, the young Earth was not a quiet place waiting for a single, miraculous spark. It was a planet alive with energy, a dynamic and powerful chemical reactor. A violent flash from the sky, a persistent bath of light from the sun, a warm, steady heartbeat from the deep. These were the forces that took the simple, floating letters of the atomic alphabet and began to slam them together, to cook them, to force them into partnerships. They were the catalysts that began to form the first simple words, the amino acids, the nucleotides, the sugars. The world was no longer just a collection of ingredients. It was now a workshop. The random dance of atoms had been given a rhythm, a direction. The great, slow, ponderous process of molecular evolution had begun. Section 3. The first humble chains. And so, the ocean, once a simple broth of salt and mineral, is now seasoned with something new. The storms and the sun and the deep-sea furnaces have been at work for millennia, and their labor has borne fruit. Drifting in the warm, primordial waters carried on the slow currents are the first words of the chemical language. Countless tiny, individual molecules of amino acids, the precursors to proteins. Simple sugars, the future fuel of life. And the first nucleotides, the humble ancestors of the genetic code. They are here. They exist. But for now, they are solitary. Imagine one such molecule, an amino acid, tumbling through the water. It is a masterpiece of cosmic chemistry, forged in lightning and starlight, but it is alone. It can do very little by itself. It is like a single letter, a single musical note, a single, lonely thread of color. It holds a universe of potential, but a potential that can only be unlocked through connection. A single letter cannot tell a story. A single note cannot create a melody. A single thread cannot be woven into a tapestry. For the next great secret to be revealed, these lonely individuals had to learn to hold hands. They had to learn to form chains. This is the simple yet profound magic of polymerization. Let us focus again on that single amino acid, floating in the warm, sunlit shallows. Like all amino acids, it has two distinct ends, two hands, with which it can greet the world. One end is an amino group, rich with nitrogen. The other is a carboxyl group, a little cluster of carbon and oxygen. It is this dual nature that makes it such a perfect candidate for connection. Now, imagine two of these amino acids drifting near each other, nudged together by the random, gentle motion of the water. By pure chance, the amino group of one molecule aligns with the carboxyl group of the other. The giving hand of one meets the receiving hand of the other. For a moment, nothing happens. They are stable, content in their solitude. But if a little energy is provided, perhaps a nudge from the sun's ultraviolet rays or the catalytic encouragement of a nearby mineral surface, something beautiful occurs. A tiny sacrifice is made to seal a new bond. The giving hand releases a hydrogen atom. The receiving hand releases a hydrogen and an oxygen atom. Together, these three lost atoms, two hydrogens and one oxygen, click together to form a new molecule of water, H2O. A single, tiny, watery tear is shed. And in the space where those atoms once were, a new, strong connection is forged directly between the two amino acids. A peptide bond. They are no longer two but one. A dipeptide. A tiny two-part chain. This process is called dehydration synthesis. A name that sounds technical but is really just a simple, poetic truth. In order to build something new, a little bit of water must be lost. It is the price of admission for complexity. And once this first handshake has occurred, a new possibility emerges. The little two-part chain still has a free amino group at one end and a free carboxyl group at the other. It can reach out and greet a third amino acid, shedding another tear of water, forging another bond, becoming a tripeptide. And then a fourth and a fifth. Picture it now, a chain beginning to grow, link by patient link. A string of molecular pearls, each one added with a tiny, watery sacrifice. This is no longer just a collection of small, simple molecules. This is a polypeptide, a new kind of entity. It has length. It has direction. And because the different types of amino acids have different properties, some are bulky, some are small, some are electrically charged, this chain is not just a uniform string. It is a sequence. It is a sentence being written in the language of chemistry. A sequence that has the potential for meaning, for function. But this raises a difficult question. The very process of creation, dehydration, involves losing a water molecule. How could this happen in a world that is almost all water? An ocean that is eager to add water back, to break these new, fragile bonds apart in a process called hydrolysis? It is a profound paradox. Life needed water, but the chemistry to build life needed to get away from it. The universe, in its quiet ingenuity, found several ways to solve this puzzle. Let us return to that shallow tidal pool on the black volcanic shore. The colossal tide recedes, leaving the pool isolated, glinting under the hot, red sun. For hours, the sun beats down. The water level drops. The amino acids and other building blocks floating within are forced closer and closer together, a huddling crowd in a shrinking room. As the water evaporates, the concentration of these molecules skyrockets. They are no longer just occasionally bumping into each other, they are packed together, cheek by jowl. The very process of drying pulls water away from them, making it vastly easier for those dehydration reactions to occur. The sun's energy drives the formation of bond after bond, creating short chains of polypeptides. Then, hours later, the tide returns, a great, gentle wave washing over the pool. It sweeps these new, longer molecules out from their rocky cradle and into the vastness of the ocean. The cycle repeats, day after day, for millions of years. A slow, rhythmic breathing, in and out, wetting and drying, a patient global engine for forging chains. Or perhaps the secret lay in a different kind of surface. Imagine the fine, silty clay settling at the bottom of a quieter lagoon. Do not think of this clay as mere mud. On a microscopic level, it is a substance of exquisite order. It is made of fine, layered sheets of silicate minerals. And these sheets have a subtle electrical charge. As the amino acids drift down through the water, they are drawn to these charged surfaces. The clay acts like a molecular magnet, a silent choreographer. It captures the monomers from the water, holding them fast against its surface. But it does more than just concentrate them. It arranges them, It holds them in just the right orientation, with their reactive hands pointing outwards, ready to connect. The clay surface becomes a template, a chemical scaffolding, drastically increasing the chances of a bond forming. The clay itself acts as a catalyst, a mineral matchmaker, lowering the energy required for the reaction and protecting the new, fragile chain from being immediately broken apart by the water. Here, on these quiet, ordered surfaces, chains of polypeptides could have grown long and complex, patiently assembled over countless years, clinging to their mineral host like the first vines on a trellis. And this was not just happening with amino acids. In other pools on other clay beds, in the warm, porous chambers of the hydrothermal vents, the same story was unfolding with different characters. Nucleotides, the building blocks of RNA and DNA, were also linking up, shedding water, forming the first nucleic acid chains. These were not chains of structure, but chains of information. A sequence of bases that could, one day, carry a message. Simple sugars were also joining hands, forming polysaccharides, chains of stored energy and structural support. The ocean is changing. Its very character is becoming more complex. It is no longer a simple soup of monomers. It is now a library filled with the first short stories of existence. It is populated by countless chains, threads, and strings of varying lengths and compositions. Polypeptides that, if they get long enough, can start to fold into specific three-dimensional shapes. Polynucleotides that carry the first, faint whispers of a code. These are the first polymers. Humble chains formed through a simple process of connection and sacrifice. They are not yet alive. They have no intention, no will of their own. But they are the essential bridge. The critical link between the utter simplicity of a single molecule and the breathtaking complexity of a living cell. The world has learned to write words and sentences. It has not yet learned what to say. Section 4. The Paradox of Water. And so, the first chains begin to form, delicate threads of possibility in the vast, ancient ocean. A universe of complexity is being born, link by patient link. But as we drift here, watching this slow miracle unfold, we encounter a profound and beautiful problem, a riddle at the very heart of creation. The problem is water itself. Water, the gentle medium of our entire story. Water, the womb of the world, the solvent of creation, the very substance that made this primordial soup possible. It is the stage, the setting, and the most abundant ingredient. And yet, this universal giver is also a patient, persistent taker. The very act of forming a peptide bond, as we saw, requires the removal of a water molecule. It is a chemistry of dryness, of dehydration. And here it is, trying to happen in an environment that is, by its very definition, the essence of wetness. Imagine one of our new, fragile chains of amino acids, a short polypeptide, floating proudly in the warm sea. It is a triumph of chemistry, a small victory against chaos. But all around it, pressing in from every side, are trillions upon trillions of water molecules. And these water molecules have a kind of memory, a relentless tendency. The bond that holds our chain together was formed by casting out a molecule of water. And the ocean wants it back. A water molecule, a tiny, angled key of hydrogen and oxygen, drifts by. It senses the slight tension in the peptide bond, the molecular scar left behind by the departed water. And it probes it. With a gentle, chemical insistence, it inserts itself, returning the hydrogen atom to one side of the bond and the hydroxyl group to the other. With a quiet, invisible click, the bond is broken. The chain is severed. The act of creation is undone. This process is called hydrolysis, literally, to break with water. And in the primordial ocean, it was happening constantly. It was the default state. The universe, it seems, favors simplicity. It favors the breaking down over the building up. This is the great paradox of water. For life to begin, long, complex chains were needed. But these chains could only be built by pushing water away in an environment that was nothing but water. It is like trying to light a match in the middle of a rainstorm. It is like trying to build a sandcastle as the tide is coming in. The forces of dissolution were immense, patient, and ever-present. How could anything complex and lasting ever arise in the face of such a formidable challenge? How did the first sparks of creation avoid being immediately extinguished by the very medium that nurtured them? The universe, in its quiet, boundless ingenuity, did not find one solution to this riddle. It found many. It discovered loopholes, havens, and temporary shelters where the chemistry of life could find a foothold. Let us revisit the places where this magic was happening and see them now not just as workshops but as sanctuaries. Feel yourself drawn once more to the edge of a volcanic island, to a shallow pool carved into the black rock. The sun, a dull red orb in the hazy sky, beats down. The colossal tide has retreated, and this pool is now alone, a world unto itself. Watch closely. The process of evaporation is not just a loss of water, it is a temporary victory over water. As the sun's energy lifts molecule after molecule of H2O into the sky, the pool shrinks. The concentration of amino acids, nucleotides, and other building blocks increases dramatically. But more importantly, the saboteur, the water itself, is being removed from the equation. Imagine the relief in this temporary dryness. For a few precious hours, the chains can form without the immediate threat of being torn apart. Dehydration synthesis can proceed bond after bond in a world that is, for a moment, dry. The sun and the rock work together, cooking the ingredients, forging longer and more stable chains. Then, as the planet continues its slow turn, the tide returns. A great, gentle wave of warm ocean water washes over the rock, refilling the pool. It sweeps up the newly formed polymers, carrying them out into the deep. Some will be broken apart by hydrolysis, yes, but some, now longer and more resilient, will survive. The cycle repeats endlessly. A great, slow, rhythmic breath. The planet breathes out, creating dryness and complexity. It breathes in, returning them to the sea. It was a cycle of trial and error, a relentless engine that used the sun and tides to fight back against the paradox of water. Now, let us sink again, away from the harsh sun and the cycling tides, down into the quiet, deep water. Let us find one of those vast beds of silted clay we imagined before. Here, a different kind of sanctuary exists. See the clay not as mud, but as a crystalline haven, an ordered refuge. The flat, layered surfaces of the montmorillonite clay are charged, and they call out to the molecules in the water. An amino acid drifts by and is captured, held gently against the mineral surface. Then another and another. The clay acts as a silent organizer, lining them up, arranging them in neat rows. It does more than just concentrate them. It protects them. Once a peptide bond is formed on this surface, the chain clings to the clay. The mineral itself acts as a shield, physically blocking water molecules from easily accessing and breaking the new bond. The clay becomes a mineral midwife, not only helping to birth the new polymer but also swaddling it, protecting it from the ravenous environment. Here, sheltered in the arms of the rock, chains could grow, link by link, over immense stretches of time, patient and undisturbed, until they were long enough and stable enough to survive on their own. And there is yet another solution, perhaps the most elegant of all. Think of the old saying, oil and water do not mix. Even in this primordial soup, there were molecules that shared this property. The ancient ancestors of fats and oils, long, greasy chains of carbon and hydrogen called lipids. These were the antisocial molecules of the ancient world. They were hydrophobic, water-fearing. While most other molecules were happy to dissolve and mingle in the ocean, these lipids turned their backs on water, seeking out each other's company instead. Picture it. In the turbulent ocean, wherever these lipid molecules were present, they would instinctively clump together. They would form shimmering slicks on the surface, or, more importantly, they would curl up into tiny, hollow spheres. Microscopic, oily bubbles. Inside one of these bubbles, a miracle occurred. The water was pushed out. The interior of this sphere was a tiny, self-contained pocket of dryness, a hydrophobic haven, existing right in the heart of the ocean. Any monomers amino acids nucleotides that happened to be trapped inside when this bubble formed were now in a perfect environment for polymerization. Safe from the threat of hydrolysis, surrounded only by other building blocks, they could link together with incredible efficiency. These lipid spheres were more than just shelters, they were natural chemical concentrators and reaction chambers. They were the perfect answer to the paradox of water, creating tiny, isolated laboratories where the chemistry of life could proceed, protected and undisturbed. So you see, the paradox was not a dead end. It was a filter. It was a challenge that forced innovation. Life could not begin anywhere and everywhere. It had to find these special places, the drying shores, the sheltering clays, the oily bubbles. These were the oases in the great watery desert, the places where the relentless pressure of dissolution was held at bay long enough for something new, something fragile, and something extraordinary to take hold. The world had learned to write sentences. And now it had found the quiet, protected libraries where it could begin to compose the first epic poems of existence. Section 5. The Memory of a Molecule. The oceans are now humming with a new kind of potential. The patient work of the sun, the shores, and the deep-sea vents has filled the water with a rich and varied population of molecular chains. Drifting through the warm currents are countless short polypeptides, the first structural sentences, and the first polynucleotides, the first informational whispers. But a profound piece is still missing from the puzzle. These chains, these humble polymers, are mindless. They are accidental creations, beautiful but purposeless. A polypeptide might, by pure chance, fold into a shape that is useful, perhaps encouraging other molecules to join together. But there is no way to remember that success. No way to recreate it. It is a fleeting, random victory lost as soon as it is won. It is a sentence written in the sand, destined to be washed away by the next tide. And this reveals a beautiful, classic paradox, a chicken and egg problem that lies at the very foundation of life as we know it. In all modern life, information is stored in the elegant, stable, double helix of DNA. DNA is the master blueprint, the library of instructions. But the instructions in the DNA are useless on their own. To be read, to be copied, to be translated into action, they require complex protein machines called enzymes. So, DNA holds the recipe for the proteins, but the proteins are needed to read the DNA. One cannot exist without the other. Which came first? The perfect library with no librarian, or the brilliant librarian with no books? For decades, this question seemed like an impassable wall. Let your mind drift in this quiet, ancient sea and feel the weight of this problem. All around you are the pieces, the amino acids that build proteins and the nucleotides that build DNA. But they cannot speak to each other. They are two different languages with no translator. The story of life seems stalled before it can even truly begin. But the universe is subtle and its solutions are often elegant in their simplicity. The answer, many scientists now believe, was not to choose between the chicken and the egg. It was to find something that was, for a time, both. The answer was a different kind of molecule. A humble genius, a jack of all trades, a forgotten hero of this early world. Its name is RNA, ribonucleic acid. It sounds complex, but its nature is one of profound versatility. RNA is a very close chemical cousin to DNA. It is also a long chain, a polymer made of nucleotides, and it uses a similar four-letter alphabet to store information. But it is different in a few crucial ways. It is typically a single strand, not a double helix. It is less stable, more reactive, more eager to get involved in the chemical world around it. And in these small differences lies the key that may have unlocked the entire future of life. RNA, it turns out, could have been both the chicken and the egg. Could have been the librarian and the library. Let us first consider its role as the library, as the keeper of memory. Imagine a chain of RNA forming in that primordial soup. Like a string of beads, it is a sequence of 4 different chemical letters, A, U, C, and G. This sequence is not random gibberish. It is information. It is a code. A particular order of these letters could be a recipe, a set of instructions for a specific task. For the first time, a molecule could carry a memory of how to be. A blueprint for existence. This is the first half of the solution. RNA can store genetic information just like DNA. It can hold the secret. But here is where the true magic happens. Unlike the stiff, ladder-like structure of DNA, which is wonderful for passive, stable storage, the single strand of an RNA molecule is flexible. It is free. It can fold back on itself, the letters in one part of the chain forming weak bonds with complementary letters in another part. And in doing so, it can fold into a specific, complex, three-dimensional shape. Think of it like a long ribbon of paper which can be folded into an intricate piece of origami. A flower, a bird, a machine. And these shapes were not just pretty. They were functional. By folding into a precise shape, an RNA molecule could create little pockets and clefts on its surface, active sites that could cradle other molecules that could encourage or catalyze chemical reactions. In essence, the RNA molecule itself could become a tiny machine, a molecular tool. It could perform work. It could function like a protein enzyme. Scientists have given a name to these catalytic RNA molecules, ribozymes. The recipe, it turns out, could also cook the meal. Now imagine the breakthrough moment. Picture a warm, protected pool, perhaps in the porous rock of a hydrothermal vent, rich with the nucleotide building blocks of RNA. By sheer, dumb luck, over millions of years of trial and error, a string of RNA forms with a very special sequence. This sequence causes it to fold into a very particular shape. And this shape has a breathtakingly new and powerful ability. Its active site is perfectly formed to grab onto other, free-floating nucleotides and help them link together, forming a new chain of RNA. More than that, it can use its own sequence as a template, guiding the formation of a new strand that is a mirror image of itself. Stop and feel the significance of this moment. A single molecule, born of chance, has learned the secret of secrets. It has learned to make a copy of itself. This is the spark. This is the transition from mere chemistry to the very edge of biology. Before this moment, success was temporary. A useful molecule was a happy accident, destined to be destroyed and forgotten. But now a successful molecule, one that is stable and good at replicating, can create a dynasty. It can make copies of itself, which can make copies of themselves. A lineage has begun. For the first time, natural selection has something to work with. It is no longer just a random dance of atoms. It is a competition. RNA molecules that, through some random mutation in their sequence, become even slightly better at copying themselves will become more numerous. RNA molecules that are more stable will last longer and have more opportunities to replicate. A new kind of evolution has begun, operating on a population of competing, replicating, and evolving RNA molecules. This hypothetical era is called the RNA world. It is a world before cells, before DNA, before proteins. It is a world run by these versatile RNA molecules. Imagine a teeming, microscopic ecosystem of them. There are RNA strands that specialize in replication, others that have folded into shapes that can cut other RNA molecules, others that can join them together. Some might even catalyze the formation of the first amino acid chains, linking the world of genetics to the world of proteins for the very first time. RNA was the perfect bridge. It was simple enough to arise spontaneously, yet complex enough to store information and perform work. It was the single artisan who could both read the blueprint and build the house. It solved the chicken and egg problem by being both at once. It was a temporary, messy, beautiful solution, a scaffolding that would allow for the construction of the more stable and efficient DNA-protein system that would eventually replace it. But for a time, perhaps for millions of years, the planet was alive with the song of RNA. It was the sound of information learning to remember itself, the sound of the universe learning to pass on its secrets. The first spark was not just of energy, but of memory. And with that memory, true heredity was born. Section 6. A bubble of one's own. The world is now alive with information. In the quiet, protected corners of the earth, the RNA world is in full flourish. a vibrant, invisible ecosystem of molecular memory, where strands of RNA compete, evolve, and learn to copy themselves. They are the first storytellers, the first librarians, passing down the fragile secret of their own existence. But this burgeoning life has no anchor. It is a kingdom without borders, a workshop without walls. Imagine one of our clever, self-replicating RNA molecules. It has triumphed in the molecular lottery. It is a master replicator. It works tirelessly, gathering the nucleotide building blocks that drift by and painstakingly assembling them into copies of itself. But in the vast, open water, this success is diluted, shared with everyone, and ultimately meaningless. The new copies it creates can simply float away, carried off by a gentle current. The raw materials it needs are scattered, and it must wait for them to drift by purely by chance. There is no home. There is no self. There is no clear distinction between the replicator and the world it lives in. For evolution to take the next great leap, for a true individual to emerge, a line needed to be drawn. A boundary had to be created. Life needed a home. It needed to separate inside from outside. The solution did not come from the clever RNA. It came from a different kind of molecule we have met before, a quiet and unassuming character that had been present in the primordial soup all along. The loner, the recluse, the lipid. Let us revisit these strange molecules. They are the ancestors of fats and oils. Unlike the amino acids and nucleotides, which happily dissolve in water, lipids are hydrophobic. They fear water. But their structure holds a secret duality, a beautiful contradiction. A lipid molecule typically has a head and a long tail. The tail is the part that is purely hydrocarbon, greasy and deeply water-fearing. But the head group is often different. It is polar. It is hydrophilic. It loves water. So here we have this wonderfully conflicted molecule. A two-faced entity with a head that wants to embrace the ocean and a tail that wants to run and hide from it. What happens when you sprinkle millions of these molecules into the turbulent, watery environment of the young Earth? They don't just float aimlessly. They are driven by the fundamental laws of physics, by their own contradictory nature, to perform a small and spontaneous miracle. They self-assemble. Picture it. As these lipid molecules tumble through the water, their tails instinctively seek to hide from it. They turn inwards, huddling together, creating a water-free core. And their water-loving heads naturally turn outwards, facing the surrounding ocean, acting as a willing interface. In the churning water, they would spontaneously form tiny spheres. But not just simple, solid balls. They would form a structure of breathtaking elegance and utility, a hollow, double-layered sphere called a vesicle. Imagine a microscopic, watery fortress. It has two walls. The outer wall is made of the lipid heads, facing the outside world of the ocean. The inner wall is also made of lipid heads, facing the small pocket of water trapped on the inside. And sandwiched between these two walls, hidden away from water on either side, are all the hydrophobic tails, finally safe and content in their own oily, water-free layer. This structure, the lipid bilayer, is the exact same fundamental structure that makes up the cell membrane of every living thing on Earth today, including you. It required no architect, no blueprint, no RNA instruction. It was a gift of physics, a shape that matter naturally falls into under the right conditions. The universe, it seems, knew how to build a container. Now imagine the fateful, beautiful accident. In a quiet lagoon, a population of these vesicles are constantly forming, breaking apart, and reforming. And in this same water drifts one of our successful, self-replicating RNA molecules along with a rich supply of its nucleotide building blocks. By pure chance, a sheet of lipids begins to curve, to fold, to close in on itself to form a new vesicle. And at that exact moment, it happens to trap that RNA replicator and a small portion of the surrounding soup inside. The bubble closes. The boundary is sealed. For the first time, a line has been drawn. This is inside. Everything else is outside. A protocell has been born. Feel the profound shift this single event creates. Inside this tiny sphere, the world has changed completely. The replicator RNA is no longer in a vast ocean waiting for a building block to drift by. It is now in a tiny, confined space, a highly concentrated private sea, swimming with the very nucleotides it needs to build its copies. Its work becomes exponentially more efficient. The librarian and the books are finally in the same small, quiet room. The copies it makes no longer drift away into oblivion. They are kept close, contributing to the family, to the lineage contained within the same protective walls. The success of the individual now directly benefits the individual. And the boundary is more than just a container. It is a shield. The delicate RNA chain and its replicating machinery are now protected from the harsh ultraviolet light, from damaging chemicals, and from other predatory RNA molecules that may have evolved to tear it apart. It is a home, a sanctuary, a private universe in a single drop of water. This act of encapsulation creates a new entity, a new unit upon which natural selection can act. Evolution is no longer just looking at the naked RNA strand. It is looking at the entire system, the membrane and its precious cargo. Their fates are now intertwined in a molecular marriage. A protocell with a slightly more stable membrane will last longer, giving its internal RNA more time to replicate. It will be selected. A protocell containing an RNA molecule that is a more efficient replicator will fill its home with copies faster. But this presents a new, beautiful problem. The problem of success. As the RNA replicates, it creates more and more matter inside the tiny vesicle. The internal pressure grows. The bubble is stretched to its limit. It needs to grow or it will burst, destroying the whole enterprise. Perhaps the membrane itself could grow by incorporating more lipids from the outside world. Perhaps the internal pressure would eventually cause the sphere to elongate and then pinch in the middle, dividing into two smaller daughter vesicles, each with a share of the precious RNA cargo. Suddenly, we don't just have replication of a molecule. We have the reproduction of an entire entity. The protocell is not just a home. It is the first ancestor of a cell. The ancient ocean is transformed once more. It is no longer just a library of floating sentences. It is now teeming with countless tiny, individual experiments. Billions of microscopic bubbles, each one a fragile hypothesis, each one a tiny, self-contained world. Each bubble contains a slightly different version of the RNA replicator, a slightly different mix of ingredients, a slightly different quality of membrane. And now the competition is between these protocells. The ones that can hold themselves together, that can replicate their contents, and that can somehow manage to divide and pass on their success will thrive. The ones that fail will simply pop, their contents returning to the public domain of the primordial soup. The world has found its first self. It is a humble, fragile thing, a tiny bubble of oil and memory. But in that separation, in that simple act of drawing a line, the foundation for all biology, all individuality, all of the complex is that would one day populate the planet was laid. Section 7. The First Stirrings of Hunger. The protocell is a masterpiece of spontaneous order, a bubble of memory afloat in a sea of chaos. Within its oily walls, the precious RNA replicator is safe, concentrated, and efficient. It is a tiny, self-contained universe, a kingdom of one. But in creating this perfect sanctuary, a new and subtle crisis has emerged. The very wall that protects it also isolates it. The boundary that defines itself has cut it off from the world. It is a king in a castle, safe from the dragons outside, but with no way to bring food in from the fields. Imagine this tiny, fragile entity. It has used up the initial supply of nucleotides that were trapped with it. Its miraculous replication grinds to a halt. The internal engine has run out of fuel. The membrane, this beautiful, self-assembled wall, is a perfect barrier. But a perfect barrier is also a perfect prison. For this new entity to persist, for it to grow and divide and truly conquer the world, it could not remain a passive vessel, a lucky trap. It had to learn to interact with the environment it had so carefully separated itself from. It had to learn to reach through its own walls. It had to develop the first, faint, unconscious stirrings of hunger. This is the dawn of metabolism. A word that sounds clinical but is, in reality, the poetry of life in motion. It is the story of how a living thing takes a piece of the outside world, breaks it down, takes its energy, and uses that energy and those pieces to build more of itself. It is the constant, dynamic dance of taking in, transforming, and building up. And for our protocell, this dance began with the simplest of steps. Perhaps the first solution was one of imperfection. The earliest lipid membranes were likely not the flawless, tightly controlled barriers of modern cells. They were probably a bit leaky, a bit porous. Think of the wall not as solid stone, but as a loosely woven curtain. While the large, precious RNA molecules, the crown jewels of the cell, were too big to slip through the gaps, smaller molecules could. Picture our hungry protocell drifting through a patch of the ocean rich in nucleotides, the alphabet of RNA. These small, individual letters, carried by the random motions of the water, could simply diffuse through the membrane, slipping between the lipid molecules. They would naturally move from the area of high concentration, the ocean outside, the area of low concentration, the depleted interior of the cell. The cell did not need to do anything. It simply had to be empty. Its own need created a vacuum that the universe, in its tendency to seek balance, would fill. The membrane was breathing, passively inhaling the ingredients it needed from the surrounding sea. The cell was feeding not through action but through a state of being. This was a profound step. The protocell was no longer just a static container. It was a system in equilibrium with its environment, constantly sipping from the primordial soup. And as these new nucleotides flowed in, the RNA replicator inside could awaken. The engine could restart. It could build new copies of itself, preparing for the great act of division. But this passive feeding, while elegant, was slow and unreliable. It depended entirely on the cell drifting through a rich patch of soup. True agency required a more active role. Let us imagine the next great evolutionary leap, driven by the ceaseless competition between these billions of protocells. Inside one of them, the resident RNA molecule undergoes a random mutation. A letter in its sequence is changed by a cosmic ray or a copying error. And this small change causes the RNA to fold into a slightly different shape. This new shape, a new ribozyme, has a remarkable ability. Part of it is able to nestle within the lipid membrane itself, creating a small, stable channel, a dedicated doorway. This is the ancestor of a transport protein. For the first time, the cell has a gate in its wall. A gate that it built itself. Or perhaps the new RNA shape did something even more remarkable. Perhaps it learned to act like a hand. It could reach out, bind to a specific nucleotide on the outside of the membrane, and then, through a change in its own shape, pull that nucleotide through the wall and release it inside. This was no longer passive diffusion. This was active transport. The cell was no longer just waiting for food to drift in. It was reaching out and grabbing it. The librarian had evolved a new skill. It had become the doorman, actively inviting its preferred guests inside. With this new power, the protocell becomes vastly more efficient. It can scavenge for resources even in nutrient-poor waters, concentrating the building blocks it needs, outcompeting its more passive neighbors. Its success is now a product of its own labor. But all this work replicating, actively pulling in nutrients requires energy. Where did the power come from? The passive warmth of the ocean is not enough. Life needed to learn to capture and control its own fire. It needed a source of usable, chemical energy. Perhaps the answer lay in a gradient, a difference between the inside and the outside. Imagine our protocell drifting near one of those deep-sea hydrothermal vents. The water inside the cell is of a certain pH, a certain chemical balance. The water spewing from the vent is radically different: hot, acidic, rich in high-energy molecules like hydrogen sulfide and free protons. This difference between the inside and the outside is a form of potential energy, like a waterfall or a coiled spring. It is a battery waiting to be plugged in. Now imagine another RNA mutation. Another new ribozyme. This one learns to let a proton from the high concentration outside slip into the low concentration inside. And as the proton flows through this RNA gate driven by the fundamental desire of the universe for balance, it releases a tiny puff of energy. And the ribozyme learns to capture that puff of energy, using it to power another reaction, perhaps the very reaction that pulls a nucleotide into the cell. It has learned to tap the planet's battery. It has created an internal economy where one process pays for another. This is the dawn of catabolism, the art of breaking things down to release their power. The protocell has learned its most important lesson yet. It has learned to eat. It is no longer just absorbing pre-made building blocks. It is taking in energy from its environment and using it. It is becoming a tiny engine, a transformer of planetary energy into biological work. The interior of the protocell is no longer a simple, quiet room. It is a bustling workshop. A complex network of reactions is emerging. Ribozymes that harvest energy. Ribozymes that bring in raw materials. And at the center of it all, the master replicator RNA, using those materials and that energy to write its own story over and over again. This is metabolism. A self-sustaining, self-perpetuating, dynamic web of chemical reactions, all contained within a simple lipid wall. The protocell is no longer just a passive object, a product of its environment. It has become an agent. It has a self that it actively maintains. It has a hunger that it actively seeks to satisfy. It has found a way to be not just in the world, but to be a dynamic, living part of it. The faint spark of memory has found a body, and that body has now found its fire. Section 8. Learning a universal language. The RNA world, now housed within its countless protocell fortresses, has reached a fever pitch of creativity. It is a world of breathtaking ingenuity, a bustling, microscopic metropolis where RNA molecules serve as architects, engineers, librarians, and foremen. They carry the genetic code, they replicate it, they build the gates in the cell walls, and they manage the first flickering flames of metabolism. It is a system that works. It has brought the planet from the silence of non-life to the hum of true, replicating biology. But it is a system living on a knife's edge. Let us feel the fragility of this world. RNA, the jack of all trades, is also a master of none. As a genetic library, it is unstable. Its single-stranded nature and its reactive chemical structure make it prone to damage and mutation. The genetic story is written in chalk on a busy sidewalk, easily smudged, easily lost. And as a workforce, its catalytic abilities are limited. The ribozymes are clever, but they are clumsy. They cannot perform the vast range of complex tasks needed for a truly sophisticated cell. The RNA world was the brilliant, improvised scaffolding that allowed construction to begin, but it was not the permanent building. For life to become robust, to spread and conquer the planet, it needed to upgrade its operating system. It needed to separate its tasks, to find specialists for its two most critical jobs, storing information and doing work. This transition from the frantic all-in-one RNA world to the more stable, elegant system we know today was perhaps the most profound revolution in the history of life. It was the moment life invented its own, universal, and eternally stable language. The specialists it found were DNA and proteins. Think of DNA, deoxyribonucleic acid. It is RNA's quieter, more stable sibling. The removal of a single oxygen atom from its sugar backbone makes it chemically more resilient, less likely to break down. Its magnificent double helix structure is not just beautiful, it is a masterpiece of information security. With two strands, each a mirror image of the other, the genetic code has a built-in backup copy. If one strand is damaged, the cell can use the other as a template to make a perfect repair. The information is no longer a single, vulnerable thread, but a protected, twisted ladder kept safe in the heart of the cell. It is the perfect library, quiet, stable, and archival. The chalk has been replaced with words carved in stone. And on the other side of the equation, there are the proteins. These are the chains of amino acids whose formation we witnessed so long ago. While RNA can fold into a handful of useful shapes, the 20 different amino acid building blocks offer a vastly greater vocabulary of structure. Proteins can fold into an almost infinite variety of shapes, creating tools of incredible specificity and power. They can be strong structural girders, tiny molecular motors, sensitive signal receptors, or, most importantly, incredibly efficient enzymes. They are the master craftsmen, the tireless workforce, capable of carrying out chemical reactions thousands of times faster and more accurately than any ribozyme. The future of life lay in this division of labor, DNA for the perfect memory and proteins for the perfect action. But this created the old problem once more: how to connect them. The DNA blueprint is written in the language of nucleotides. The protein machines are built in the language of amino acids. They are still two different worlds. The system needed a translator, a bridge. And the molecule that took on this crucial role was the one that had started it all: RNA. RNA did not disappear. It was not discarded. It was promoted. It became the essential middle manager, the messenger, the diplomat moving between the two great, specialized powers of DNA and protein. The new system worked like a beautiful three-act play. In Act 1, a protein enzyme, itself a product of this system, gently unwinds a small section of the archival DNA library. An RNA copy of this specific gene is made. This is not a full copy of the entire library, but just a single page, a single recipe. This short-lived, disposable copy is called messenger RNA or mRNA. Its job is to carry the instruction from the safety of the DNA library out to the bustling workshop of the cell. In Act 2, this mRNA message arrives at a magnificent molecular machine, a structure called the ribosome. And the ribosome, in one of the most beautiful echoes of the past, is itself built primarily from RNA-ribosomal RNA or rRNA. The old ribozyme has found its ultimate job as the core of the great translation factory. The ribosome clamps onto the mRNA strand and begins to read its sequence of nucleotide letters, 3 at a time. And this is where the final, crucial piece of the puzzle, the true translator, enters the stage. In Act 3, small, cloverleaf-shaped RNA molecules called transfer RNA, or tRNA, arrive. Each tRNA molecule is a perfect linguistic bridge. At one end, it has 3 nucleotide letters that recognize and bind to a corresponding 3-letter word on the mRNA. And at its other end, it carries a single specific amino acid. Imagine the scene at the ribosome. The mRNA slides through like a tape. The ribosome reads a 3-letter word, say CAG. A specific tRNA molecule, the one whose code recognizes CAG, flies in. Attached to its other end is the amino acid glutamine. The ribosome takes the glutamine and adds it to a growing chain of other amino acids. Then the ribosome moves to the next word on the mRNA tape. AUG. The tRNA that recognizes AUG flies in, carrying its passenger, the amino acid methionine. The ribosome adds the methionine to the chain. Word by word, codon by codon, the message written in the language of nucleotides is being translated with perfect fidelity into a sentence written in the language of amino acids. Protein is being born. This system, the flow of information from DNA to RNA to protein, is the central dogma of molecular biology. And the key that unlocks it, the Rosetta Stone that makes it all possible, is the genetic code. The dictionary that says CG means glutamine and AUG means methionine. The fact that this code is essentially the same, universal for every single living thing on this planet, from a bacterium to a blue whale to you, is the single greatest piece of evidence that all life shares a single, common origin. This was the moment life became truly universal. It had discovered a language so powerful, so elegant, and so stable that it would never have to be reinvented. The frantic ad hoc experimentation of the RNA world gave way to a system of immense clarity and power. The protocell was no longer just a bubble of memory. It was now a tiny, self-perpetuating temple of information, where an ancient, sacred text written in DNA was being continually read, translated by RNA, and expressed as the living, breathing work of proteins. The secret of existence was now written in a language for the ages. Section 9. The Great Ancestral Community. And so, the New World Order is established. A silent, elegant pact has been forged between DNA, RNA, and protein. In countless tiny protocells scattered like dust in the immense, warm oceans, the same fundamental miracle is playing out. Information, stable and secure, is being transcribed, translated, and turned into the living, breathing work of existence. This was not an isolated victory. It was a planetary revolution. The invention of this universal language was so powerful, so advantageous, that it would have spread like a benevolent fire, sweeping away the older, clumsiest systems of the pure RNA world. Let your mind drift now into this world. Approximately 3.8 billion years ago. The planet is still alien, with its hazy orange sky and its vast, iron-green oceans. But the water is no longer just a soup of chemicals. It is a living broth. It is teeming with these newly sophisticated protocells. These are the first true bacteria, the first archaea, the pioneers of the new age. And if we trace the lineages of all life on Earth today, every plant, every animal, every fungus, every microball of our genetic roads lead back to this one point in time. They converge on a single common source. We give this source a name, LUCA, the last universal common ancestor. It is a name that sounds like a person. It evokes the image of a single heroic cell, a microscopic Adam or Eve, from which all subsequent life descended. It sounds like a single trunk at the very base of the great tree of life. But this image, while simple, is probably not the truth. The reality is more fluid, more communal, and, in many ways, far more beautiful. LUCA was likely not a single organism. LUCA was a conversation. It was a global community. To understand this, we must remember the nature of these first cells. They were triumphs of engineering, but they were still fragile. Their membranes, while functional, were not the perfectly sealed and regulated barriers of modern cells. They were leaky. They were prone to breaking. Life was a precarious, messy affair. In the turbulent waters, cells would constantly burst, spilling their precious, newly evolved genetic contents into the surrounding ocean. Their DNA, their masterful proteins, their clever RNA translators, all of it would pour back into the public domain. Now imagine another nearby cell, a survivor. It drifts through this cloud of genetic debris, and through the pores in its own imperfect membrane, or perhaps using a newly evolved protein pump, it absorbs a piece of this free-floating DNA, a gene from its fallen neighbor. This is a form of inheritance that is utterly alien to us. It is not the clean, vertical transfer of genes from a parent to a child. It is a horizontal transfer. It is the sharing of secrets between neighbors, between strangers, even between distant cousins. It was an inheritance not of lineage, but of community. Think of it as a vast, planet-wide marketplace of ideas. Each cell is a small workshop, experimenting, innovating. One cell, by random mutation, might develop a gene for a brilliant new protein that can harness energy from sunlight. Another, on the other side of the world, might invent a more efficient way to repair its DNA. In our world, these innovations would be passed down slowly, generation by generation, confined to a single family line. But in the world of LUCA, these genes were not confined. When the cell with the sun-harvesting protein burst, its revolutionary gene was released into the water. Other cells could pick it up, incorporate it into their own genome, and immediately gain this new superpower. The recipe for this invention could spread horizontally like a rumor, like a shared piece of wisdom, across the entire global population in a geological blink of an eye. The whole community could learn and evolve together. LUCA, then, was this global, fluid gene pool. A planetary superorganism bound together by the constant swapping and sharing of its best ideas. The last universal common ancestor was not a single cell, but the state of this communal world just before it began to change. It was a time when the boundaries between individuals were still blurry, when the very definition of self was negotiable. The entire ocean was a single, planetary mind collectively solving the problems of survival. This era of open-source biology, of rampant horizontal gene transfer, is why the very base of the tree of life is so difficult for us to see. It is not a single, clean trunk. It is a tangled, interwoven root system, a web, a network. The legacy of LUCA is not a single set of genes, but the core consensus toolkit that this entire community agreed upon. The universal genetic code, the ribosome for translation, the use of DNA for storage and proteins for work. These were the foundational technologies, the operating system that was so successful it became the standard for everyone. But this open, communal paradise could not last forever. As evolution continued, driven by the relentless pressure of selection, a new innovation would have emerged. A better cell wall. A stronger, more secure, less leaky membrane. A cell that could protect its own hard-won genetic innovations from the outside world and stop them from being shared freely. This was a profound and necessary act of selfishness. A cell with a better wall would be more stable. It would lose fewer of its resources. It would be more resilient to environmental stress. But it would also become more isolated. The doors to the global marketplace were slowly closing. The frantic, horizontal swapping of genes began to slow down. Vertical inheritance, the passing of genes from parent to child, became the dominant way of life. The individual had finally triumphed over the collective. This was the moment of crystallization. The hot, molten, fluid state of the LUCA community began to cool and harden into distinct lineages. The great, single river of life began to diverge, splitting into the three great domains that we know today, the bacteria, the archaea, and our own ancestors, the eukarya. The tangled root system had finally given way to a true, branching tree. The great conversation had broken into smaller, more private discussions. But every branch on that tree, every leaf, carries the memory of that shared beginning. Deep within your own cells, at this very moment, the same fundamental operating system that was hammered out in that ancient global community is at work. The language is the same. The machinery is the same. You are a direct descendant of that great ancestral community. Your existence is built upon the foundation of a shared, planetary wisdom, a time when life's first instinct was not to compete, but to share. You are not an island. You are the culmination of a 3.5 billion-year-old conversation. Section 10, a universe waking up. And so here we are, at the end of our journey through the deep past, and at the quiet beginning of a night's rest. Let your awareness return, for a moment, to the gentle reality of your room, the softness of your bed, the steady, quiet rhythm of your own breathing. This breath, this simple rise and fall of your chest, is the latest word in a story that began in fire and silence 4.5 billion years ago. We have been telling the story of the first spark. But the truth is, we have been telling the story of you. Let us start, for the last time, not with the earth but with the stars. Long before our sun was born, other suns lived and died in brilliant, explosive farewells. In the unimaginable heat of their stellar cores and the violent creativity of their supernova deaths, they performed the great cosmic alchemy, forging the simple hydrogen of the Big Bang into the heavier elements. They created the carbon that would become the backbone of every chain, the nitrogen that would stabilize every code, the oxygen that would one day power every breath. The stardust from these long-dead suns drifted through the blackness of space for eons, a cold, silent cloud of potential. And then, a small part of that cloud collapsed, ignited, and our solar system was born. That stardust, the very ash of the cosmos, fell upon a young, restless world. And on this primordial canvas, the universe began a slow, patient process of waking up. It began to learn. First, it learned the simplest chemistry. With the raw energy of lightning and the young sun, it learned to take the letters of the atomic alphabet and form the first simple words. The amino acids, the nucleotides, a vocabulary of existence. Then, on drying shores and in the shelter of mineral clays, it learned to string these words together. It learned to write the first sentences, the first humble polymers, sacrificing a little of itself, a tear of water with every new connection. But these sentences were meaningless without memory. And so, in the genius of a single molecule, it learned the secret of replication. In the RNA world, the universe learned to remember, to pass on its successes, to create a lineage. It learned to tell a story that could last. This story needed a home, a sanctuary. So with the simple physics of oil and water, the universe learned to build walls. It created the first protocells, tiny, private worlds that separated self from other, allowing the story to be nurtured and concentrated. Inside these homes, it learned to hunger. It learned to build gates in its walls, to draw in fuel and materials from the outside world. It learned the dance of metabolism, the art of turning a piece of the planet into more of itself. It learned to power its own existence. And finally, to protect its story for the ages, it learned a universal language. It discovered the perfect stability of DNA for its library, the perfect versatility of proteins for its workforce, and the perfect diplomacy of RNA to translate between them. It established a system so robust and beautiful that it has never been replaced. This system, this living code, was shared and refined in a great global community, our last universal common ancestor. And from that ancient, communal wellspring, a single, unbroken thread of life spools out through the immense darkness of geological time. Imagine that thread. It has survived the bombardment of asteroids. It has endured planet-freezing ice ages and periods of intense volcanic fire. It has persisted through mass extinctions that wiped out nearly all other life. For almost 4 billion years, this thread of replication, of information being passed from one generation to the next, has never once been broken. And the end of that thread, the living, breathing, current tip of that ancient, cosmic vine, right now is you. Every cell in your body is a direct, physical descendant of those first protocells. The DNA coiled tightly in your nuclei is a library containing chapters written in the age of LUCA. The ribosomes translating that code at this very moment are using the same universal language that was first perfected in those primordial seas. The salt in your blood is a faint chemical echo of the ancient ocean. The iron that carries oxygen through your veins was forged in the heart of a star. For billions of years, this process unfolded in silence. It was a story with no one to read it. A symphony in an empty hall. Life replicated, it evolved, it grew more and more complex. It created forests and coral reefs and creatures of breathtaking beauty. But the universe still had no way of knowing what it had done. And so it took one final, miraculous step. On one small branch of that great tree of life, the cells of the nervous system began to connect in new and ever more intricate ways. They formed a brain. And this brain, this web of electricity and chemistry, learned to do something new. It learned to hold an idea. It learned to remember the past and imagine the future. It learned to wonder. It learned to be conscious. You are not separate from this story. You are its culmination. The consciousness with which you are hearing these words is the universe's way of finally waking up and looking at itself. The sense of awe you might feel is the cosmos reflecting on its own improbable, beautiful journey from rock and water to thought and feeling. The curiosity that brought you here tonight to ask, how did it all begin, is the universe asking that question about itself through you. You are a collection of stardust that has learned to think. You are a piece of the ancient earth that has learned to dream. All the chaos and all the silence, all the patient chemistry and all the violent energy has led to the quiet miracle of your awareness here, now, in this peaceful moment. Our journey tonight comes to a gentle close. We have traveled from the very edge of nothingness to the dawn of life, a story that is both infinitely vast and intimately personal. Let these cosmic thoughts now settle and dissolve like grains of sand sinking through a deep and quiet ocean. There is no need to hold on to them. The story is already a part of you. The ancient, life-giving chemistry sleeps within your cells and it will be there when you wake. For now, there is nothing left to do but rest. Let your mind drift on the slow, dark currents of sleep, secure in the knowledge that you are a precious, thinking, dreaming part of a universe that is waking up. Sleep well. Dream deeply. Good night.